So here we have question 8, and we're asked to use linear interpolation to estimate our interquartile range. Okay, new thing here, interpolation. What does that mean? Okay, often students have a formula to do with this, but I like to kind of teach the understanding behind it, which I think is a bit stronger. Okay, so at the moment what we have, okay, is we've got data that tells us there's 5 students that have run with a time between 20 and 29 minutes. Okay, but we don't know where these students are. Okay, you could have 5 students here, or you could have one, two, three, four, 5. Okay, what we're doing when we use interpolation, we just assume that we have these students at a regular interval. Okay, so they're evenly distributed along that line. I know that wasn't very good evenly distribution of my lines, but the key thing here is this difference is always the same. Okay, and that's what the formula is doing. It's calculating the difference such that this is the same. Okay, perfect. All right, now a key mistake in this question is if you're looking at this table, where would you put someone who ran at a time of 29.6? Okay, you don't know at the moment where you'd put them. Okay, so the rounding here is rounded to the whole minute, basically. Okay, so this would be put in 30. Okay, but realistically, we've got ranges of 29.5. Okay, um, is actually going on here to 39.5. Okay, so keep that in mind, which is key and which will help us for our interquartile range. If that didn't make sense, don't worry, I'm going to show you that now. Okay, so first we've got 80 data points. Okay, if we add all of these together, we have 80. Okay, that makes the calculations easy. 80 times a quarter is 20, which is our lower quartile. 80 times 3/4 is 60, which is our upper quartile. Okay, this is the frequency at which our upper quartile or lower quartile data point occurs. Okay, so where is the 20th cumulative frequency? Okay, it's in this range. Okay, what is that range? Well, from what we explained here, that range needs to be 39.5 all the way to 49.5. Perfect. Okay, now they're evenly distributed, so each gap, what is each gap worth? Well, there's 36 kind of gaps, so 1 over 36. Okay, it represents one gap's worth. All right, and then we're timesing this by the total length. Okay, which is 10. Okay, because 49.5 take away 5, 39.5 is 10. Okay, so each gap is 1 over 36 times 10. That's its distance across. Okay, because we've got 36 of them, each with a distance of 10. Okay, if you were to do this 36 times, if you were to times this by 36, we end up with our distance of 10, which is what we need. Okay, so that's kind of reverse engineering what we want for this even distribution. Okay, now what do we want? We want where the 20th cumulative data point is. Okay, now we've already gone 5 in the first one, 10 in that, so we need 5, the fifth one into this range. Right, hopefully that makes sense. Okay, because you've got 15 cumulative beforehand. These two are 15, so to find 20 cumulative, you need plus 5. So the fifth one in are 36. Okay, so we then represent that by, well, we need to times this by 5. Okay, but let's see our equation. So you started at 39.5, and then you're adding on 5 lots of what one jump is. Okay, and that's our formula. Right, that's what we're doing for our formula. Okay, so we got 39.5 plus 5 lots of what one jump is, which we kind of reverse engineered, which gives us 40 point kind of 8 recurring, 8. So we'll just say 40.89. Okay, that's our lower quartile. Now we'll do this a bit quicker for our upper quartile. So we need cumulative frequency of 60. Okay, let's go up to here. Where will that be? Well, at the moment we're at 51 up to here. Here is 51, so it's going to be in the 50 to 59 range, but it's not actually 50 to 59, remember? It's 49.5 to 59.5. Okay, how many data points do we have? We have 20. Okay, so 1 over 20 times 10. That represents one jump. Okay, this represents one jump. Okay, because when you do 20 jumps, if you times this by 20, you just get 10, which is the total distance you want to have travelled after our 20 jumps. Okay, so for this is one jump. Okay, one jump is 0.5 in this case. Okay, that's a nice number to work with. Okay, so when you're starting at 49.5, how many jumps do we want to do? Well, we're at 51 here, so we want to get to 60, so we do 9 jumps. Okay, so we do 9 jumps, where each jump is, well, 10 over 20, which is just 0.5. Okay, but let's write it out like we didn't know that nice number formula there. Okay, and then we plug all this into our calculator, so 49.5 plus 9 lots of 0.5, which gives us 54. Okay, so then we find our interquartile range, we do 54, take away 40.89. Okay, and we get our interquartile range is 13.1. Okay, and remember, we've got to remember our units, so we put minutes. Alright, perfect. Let's move on to part B now. I don't know why I had that whole thing in red, that was quite ominous. Let's move back to blue. So variance and standard deviation. Again, we want to estimate this. Why is it an estimate? Well, we're using the midpoint of each class. Okay, because we don't actually know if they're evenly distributed. So if all our data was here, like we said before, then using the midpoint isn't a real good representation for our variance and standard deviation. Okay, but we're just assuming, that's why it's an estimate, assuming that our midpoint is kind of a good thing to use here. Okay, so using our formula for variance, we get that variance, we know, is going to be our sum of fx squared over our total, take away our sum of x over n squared, which is our mean. Okay, our mean squared. So f of x squared, what is that? 183,040. 183,040 divided by 80. Take away, I forgot what that term is, so I'll look back up now, but I'll add in what I know. 3740. 3740. Okay, plug this all into our calculator, so 183,040 divided by 80, take away 3740 divided by 80, all that squared, and we get 102 to 3 significant figures, but I haven't rounded yet, kept that in my calculator, square root that, I get 10.1 to 3 significant figures. Okay, and those are our two answers.